Hey folks, this is Nathan Jones here to talk to you about object-oriented programming in C. Believe it or not, it is not only possible to do object-oriented programming in C, but it's also encouraged. Today, we are going to start by talking about what object-oriented programming is and why it's useful even for C programmers. And then we'll talk about the four elements that are part of OOP, which include abstraction, encapsulation, polymorphism, and inheritance. I'll show you several techniques to be able to incorporate each of those concepts into your C code, although inheritance is kind of a big one. So that last topic, I'll show you enough concepts to understand the technique, and then share with you some resources that you can study further, since that could probably be its own full talk in and of itself. If you'd like to follow along with me as I'm showing you some of these examples, you can go to github.com/NathanCharlesJones/comparison of OOP techniques in C. All right, so what is object-oriented programming? Well, in a nutshell, object-oriented programming treats everything in software as if it were a class or a module. And the idea of a class is that I'm taking pieces of data that are related to each other and putting them inside one kind of unit alongside some number of functions that are being used to operate on that data. OOP has, like I mentioned, four kind of precepts. We're going to bundle the first two together, abstraction and encapsulation, since they're very related. Polymorphism will actually separate out into two because it's much easier in C for us to do polymorphism at build time when we compile our project than to do polymorphism while our software program is running. And then lastly, we'll talk about inheritance. So the idea of abstraction encapsulation, abstraction is the idea that I'm operating on a piece of data or a class, and I don't exactly know how it's implemented. It's kind of abstracted away. So here you can see a picture of kind of a generic toggle switch, and I don't exactly know which version is implementing this thing, but it shouldn't really matter to the calling code. I just know it's a toggle switch, and so I can toggle it. Encapsulation is the idea that I've got functions together with data that they operate on in a unit, and that I don't necessarily need other modules or other functions to be able to make this thing work. So if I've got a toggle switch, then I should be able to do toggle switch things with that class, and I shouldn't need a whole bunch of other stuff to make it work. Polymorphism is the idea that I can write code which behaves differently under different circumstances. And build time polymorphism is the idea that I can write my source code, my C code, that doesn't really change at all, and provide slightly different configuration information to the compiler or the linker to generate different executables, different binaries that behave differently. Runtime polymorphism is the idea that I want these objects to behave differently while the program is running. So you can see kind of a generic example here of creating generic shapes. In one case a square, in one case a circle, and I want to be able to call the same function on both and have two different things happen. We'll look at that. That'll actually probably be where we spend the majority of our time in this presentation. And then lastly, inheritance is the idea that some of my classes can best be described as specific instances or specific types of a more generic class. And as you can see here, kind of a silly inheritance structure that starts with animals. Ducks and dogs are two specific instances of animals. Labradors and poodles are two specific types of dogs. And in OOP languages, you can create this inheritance structure with your classes. Okay, what's interesting to me is that the first two up top here, abstraction, encapsulation, and build time polymorphism, are really just aspects of good modular code. If you think of code that is abstracted, it's encapsulated, that you can sort of swap implementations out at build time. That just describes code that's really modular. Modular code's been really well studied. It's well established that modular code is easier to design, it's easier to write, it's easier to change, it's easier to test. And so a big takeaway that I hope you get from this talk today is are just some techniques to be able to write better modular code, even if it has nothing to do with classes and inheritance and stuff like that. The two at the bottom, in my own terms, I would kind of consider these as enabling type agnostic code. And that means that, more so than the two up top, the idea of runtime polymorphism and inheritance allows us to write code which truly does not care or does not know the specific type of object being operated on. And what this does is it encourages code reuse so that we can write sort of parts of our code, parts of our application that don't change even when underlying data types or underlying classes change because the code rewrite is very type agnostic. And to not an exclusive extent, but to a much greater extent than the first two, runtime polymorphism and inheritance allow us to implement the design patterns, the classic design patterns like that are in the Gang of Four book and stuff. We can definitely do some of those with even just sort of build time polymorphism, but to a much greater extent with runtime polymorphism and inheritance, we can build out these design patterns. So this is our goal today. We'll spend a chunk of time hopefully just helping you learn how to write good modular code. And then we'll spend the second half of the presentation showing you how we can write code that is more type agnostic, that even allows you to start playing around with the classic design patterns. Okay, so let's start with this idea of abstraction and encapsulation. To start with, I'm going to show you a file which is not encapsulated, not abstracted. So let's just say I'm going to create a simple duck kind of class or object. It's got a name, and we can initialize it with the name, and we can show that name. So I'm going to go to some sample code here. And here you see I've got my duck. I'm putting it in a struct, so I can treat this like a little object, and it just has a name, right? I can create a duck with a name. I can show that duck, and for completeness, I can destroy that duck. So you can see here in the sample code that I am creating a couple of ducks. I'm going to show them, and let's see if I can run this for you real quick. Okay, so here's the output. You can see I'm initializing some ducks. I'm showing them, which is just to sort of print their names and a little message. But I'm also accessing their names directly. And so this is not showing to me, it's not showing abstraction, it's not showing encapsulation, because this main function has access to the whole object. It's all laid out. And so, if I want to reach in directly to sort of print or manipulate this name, I can do that. And even though you might argue that having the name inside a struct is somewhat encapsulated, I would argue that it's, it being all in the main file is not making any sort of module. So let's improve upon this. We're going to do this in two ways. I'm going to start by showing you how to make what's called a singleton. A singleton is a class for which there is only ever one instance. So you can imagine writing code for a microcontroller that is interfacing with a sensor. There's only ever one sensor that's attached to that microcontroller, then that might be a good example or good usage for a singleton. And so in this case, I'm modifying my class diagram slightly. You'll notice that my main function here has the number 1 to indicate that there's only ever one of these things. And you'll notice I've got a little minus sign in front of the member variable name. That's to indicate that it's now private. So the fact that this is stored as an array of characters is hidden from the programmer. And here's what this kind of looks like in C. All right, so I'll start with my header file. So you'll notice, actually I'll start with my main file. You'll notice there's nothing in here that's related to ducks. I'm just using the duck stuff. So all that got moved into my header file, duck.h, and my source file, duck.c. So duck.h is really the only kind of piece to this module that is made publicly available, like to the main function. And so other than sort of allowing the user to kind of specify how long the name is allowed to be, there's only two functions that are exposed to them, which is to initialize the name, to show this duck. That's it. They're not allowed to manipulate the name directly. They're not allowed to make additional ducks. They can only have these two functions. And so in duck.c, I'm not using a struct anymore, but by virtue of this variable being inside the source file, it effectively is hidden from the rest of the program. Even if I have access to the source file, my main file can't refer to this variable necessarily directly, because the compiler would start to complain. And by virtue of the fact that there's just one of these things, I'm able to make this little singleton where, there's only ever one that exists. It's in my source file. And I'm controlling the access to that variable by only exposing a couple of functions. Now, in some cases, I do want there to be multiple instances of an object. So you'll notice here main now doesn't have a 1. It's got a little asterisk next to the duck class because I'm indicating that I want there to be multiple ducks. In this case, I will go back to putting my information in a struct. And I have the little problem where I don't want to expose the details of this struct to the rest of the program. But I need to give the C compiler enough information to be able to create object files that use this information. So the trick here, you'll notice on the left, is that in duck.h, I'm going to use the typedef keyword to create a variable type, which is a pointer to this struct, which I'm not going to sort of put in the header file. It's kept hidden. Having the pointer is sufficient to let the C compiler generate code for like my main file that will use the duck class, because the C compiler knows the size of a pointer. And so now in all of my code, I just have to reference sort of these pointers to these structures that I operate on. So here's what this looks like in my code now. Okay, I'm gonna start with my main file. Okay, so you'll notice here now I can create multiple different types of ducks. And I can do some functions on each one of them. You'll see I'm passing the variable name of each duck to these functions to be operated on. And I can't, there's a little comment here that I can't access the name directly because that's hidden away in the struct. So let's see how I do that. Duck.h just got a little bit more complicated. You see my typedef here where I create this pointer to struct. That's what lets my main file sort of get compiled without having the full information of what's inside this structure. And you'll see I've got now a function to create new ducks as well as make them quack and show them. Here's what this looks like in my source file. So I'm creating a structure with the member variables that I want to store for each of my duck objects, which in this case is just a name. In my new function, I'm going to create new ducks on the heap using the calloc function, and I'm given the name, I'm going to copy that into each structure and return that back. And now when I do something like I make a duck quack or I show this duck, I can reference that individual duck directly using this pointer to each sort of individual duck. So here, when I call duck quack on this duck called Huey, what I'm getting is a pointer to a spot in memory where I previously created a duck and had the letters Huey copied into this array. And so then I can reference that inside this function. I've got a little assert also at the front here just to make sure that the pointer being passed into this function is non-null and that the name was created for, just as a security kind of measure. And so, so I can do that to create what are called opaque structs, right? The opaque refers to the fact that the struct is hidden inside the source file, that the details of that struct are not made known to the main function. Instead, my main function only sort of gets to operate on pointers to these structs. And since it doesn't know the internals, then it's only the functions that are listed in the header file that it gets to use on those pointers. All right, I want to make a quick note about memory management. You saw in the code just now that we were using calloc to create new objects on the heap. That's the easiest probably implementation, but definitely for a lot of embedded applications, the heap is verboten. And so another alternative is to use static memory. And the best way to do this is to create an array of ducks. You can see an example kind of up here in the upper right. And then inside our functions where we make a new duck, we effectively just have to kind of iterate through our array to find an element that's not being used. So you see here that each array element might have a space to store a duck object, and additionally some sort of Boolean flag to indicate whether that structure is being used or not. And down here in the pseudocode, basically we're going to iterate through each element in the array to see if there's one that's not in use. And if there isn't, then that'll become sort of the pointer to that structure, and the array becomes the pointer that we give back to the user. Okay, so believe it or not, even with just these two techniques, right, making singletons, making opaque structs, you can do a lot. This book right here by Bruce Powell Douglas called Design Patterns for Embedded Systems in C has a number of great kind of just techniques and patterns that can be useful for embedded programs. And unless I'm mistaken, there's nothing more complicated than the two techniques we saw that are in use in this book to be able to implement those design patterns. Additionally, if you go to the GitHub repo, you'll see an example of me implementing what's called the mediator pattern using just the two techniques we've talked about so far. Okay, let's talk about build time polymorphism. So again, in this case, we're going to try to use either the compiler or the linker to generate executables that behave differently without really messing around with our source files too much. We'll start with the linker because to me that one's a little simpler. So you can see here on the bottom left is a little diagram of how an executable file gets built. If I have a number of source files, initially the compiler will turn them into object files, and it's the linker that will take all those object files plus any library functions and array them all in memory properly to create the final executable. So it's possible to have source files that have the same function as long as we don't give both of them to the linker. You'll notice here in my little pseudocode up top that I have a source file which is using this function called object_function1, and it's defined, or it's declared here in object.h. And you'll notice to the right that I have two separate source files that both provide implementations of that function. Now, if I gave both of those source files to the linker, I'd of course get an error that said, hey, this function was defined in multiple locations. So the trick here is to give only one of them to the linker. If I don't give source file number 3 to the linker, but I do give source file 2, then this function will add 1 to whatever value it gets. And so you can see here in my pseudocode, if I call the function with the argument 5, the return value is 6. But if I exclude that function, and instead I give the linker the other one, the linker will happily sort of use that function to implement object function 1, and now the variable x will get 7 instead of 6 because now I'm adding 2. So just by using the linker to sort of include one of many possible function implementations, I can get some sort of polymorphic behavior. And this is really useful to make something called a functional simulator. And so I'm going to show you how we can use linker substitution to take an embedded application I'm trying to write for a microcontroller and test it out on my desktop computer. Now, before I show you that project, I want to make a little note because I'm going to start to change the diagramming here briefly. So previously you saw kind of the diagram in the upper right hand where I had a class that had some member variables and functions or methods that I could apply to that class. I'm going to redraw that. You can see here kind of in the bottom left because we're going to start to see how we have header files that are given multiple implementations from my source file. So it makes a little more sense to me to represent the header file as if it were like an interface class where this is just defining the functions that the C files need to implement. And I'll use the keyword implements here to kind of show how one or more C files might sort of implement the interface that's defined in my header file. All right, so here's a simplified example of that. Like I said, what I'm going to try to do is build an embedded application to be able to run more or less unchanged on my desktop. So you can see here that my main file is going to have sort of build time polymorphism with this interface that I'm calling my hardware platform. I'm going to have 4 generic functions that I want to be able to, my hardware to be able to implement. And I'm going to provide 2 implementations of those hardware functions. So I'm going to go now to this GitHub. You can follow along if you'd like by going to github.com/NathanCharlesJones/generic makefile based project for x86 and STM32F1. Forgive me, it's a mouthful. And so that'll take you here. This was the culmination of working through the Build Systems course on embedded artistry, which I highly recommend. So forgive me if the make file is a little busy. But the key part comes down here. Let me see if I can find it right here. Okay. So this makefile expects the user to type an argument, whether the target is x86 or STM32. And in my makefile here, if the target is x86, then I'm going to add this source file that provides the laptop implementations of that hardware stuff to the linker. And if the target happens to be STM32, then instead of that file, I'm going to add all of these, which provide the STM32 implementations. And you can see here in my make file, or sorry, my main code, right? I'm including hardware API.h. That's like my interface hardware file. And I've got some generic hardware functions. I'm just going to initialize the hardware, toggle my LED, delay a second, and do that infinitely. And so my hardware folder is where I sort of put this stuff. The header file, you can see here just has those generic functions that I want to be able to implement. And it's in my source folder that I provide by two different implementations. So under x86, I have an x86 source file that doesn't really do any hardware initialization. And instead of toggling action LED, it just prints something to the console and uses the sort of time spec library to implement this 1 second delay. As opposed to my STM32, which of course has a bunch more files to it. And I used CubeMX to generate this after things get after things get initialized. Here I'm defining my hardware specific functions where I toggle the LED, which is an actual LED in this case on the STM32, and I use the HAL delay function to provide me my two delays. So I'm going to skip a demo, but I encourage you to check that out. You can, even without the STM32, you can download the code there and run the x86 version and see how the same main file is implemented in two different ways. And if you have the STM32, you can see how you can program that and run it on the board kind of unchanged. Okay, so the second way we're going to use build time polymorphism is using the preprocessor. And so in this class diagram, you can kind of see I have two different source files with two totally different header files, and they are both implementing sort of this generic object class. So here's what this looks like in our source file. You notice in a specific source file, I'm going to bring your attention down to the bottom now. I'm creating a generic thing of type object, and I'm going to use this syntax here to kind of call some initialization function on this object. And the magic happens right here with these preprocessor macros. So you'll see here, if I define the symbol object1, then this source file will not only include object1.h, it'll also replace every instance of the all caps object keyword with this specific data type. And it'll look for any sort of function like macros, right? Or this is a function like macro. So it'll look for the obj parentheses, which indicates that we're kind of trying to call a function. And the first thing it's going to do is use the two pound signs here to form a concatenation, right? So it's going to see this code here, and it's going to replace this whole thing with, if object1 is defined, object1 underscore combined with whatever function names. That's the first argument here in this little list. And then I'm going to use the variadic macro. So these little ellipses here say, hey, whatever comes after this in this pseudo function list, those become the arguments to this function here. If object1 symbol is not defined, then it's object2 that sort of replaces all these generic things. So here's what this looks like in my code. If above this I pound define object1, then my code below, after the preprocessor sort of scans my file, it turns this all capitalized object into pObject1, because that was this sort of text replacement line here, this pound define. Additionally, this kind of generic object init data here becomes object1 underscore init, and new object and 5 are the arguments that are then given to that function. If I instead define object2, then the same code gets preprocessed using these lines, so everything sort of changes to the object2 version. So I can sort of, at the top of my source file, define object1 or object2 to change how I want this sort of generic object to be, processed by the preprocessor. Now, the only hiccups, of course, are that the functions sort of have to abide by this kind of naming syntax in order for these macros to work. Additionally, this pound define kind of has to be in the source file If it's in a header file, then there's the risk of like this pound define like propagating through multiple source files as headers get included, and then things get a little weird. So there's a couple of restrictions on this, but now this lets me do the really cool thing of applying build time polymorphism to just a single source file. Even though to me using the linker is a little bit easier, the downside is it's kind of a sledgehammer, right? If I link in one function, I can't link in any others, and so any polymorphism applies to the entire project. Whereas with the technique we just saw, to me it's a little more complicated because there are a couple of restrictions on how I'm allowed to use the preprocessor. But what this lets me do is specify within single source files, so what type of object, if you will, I want to use in that specific source file. Okay, let's look at runtime polymorphism now. And actually, the last thing I'll say about these is that if you go onto the GitHub, you will see two examples of using the linker and the preprocessor, two additional examples that show you how to use that for sort of a little sample problem. Okay, let's talk about runtime polymorphism. This is a big one. It's really neat, but it's also very complicated. The goal here is to be able to call a function on two different objects and have them do different things. So I'm going to start by saying this is very or hinges sort of on this idea of function pointers. So maybe this is familiar to you. If not, I want to make sure we understand what's going on with function pointers. So you see here in this sample code, up at the top, change this function is a variable. I'm declaring this variable as a pointer to a function, and the signature of the function that it's pointing to is a function that takes void and returns void. So any function that abides by this signature can be assigned to this variable called change this function. You'll notice underneath this, I have two functions which both take void and return void, so they match this function signature. And in my little main function here, you can see that I'm taking this variable, the change this function variable, I'm assigning it to one function, calling it, assigning it to the other function and calling it, and what you'll see is that I get two different answers from each one. All right, so here's this code here, and if I run this in my little replit, you'll see that after the first function call, I get hello, which was the result of this function, and then goodbye. So so this is very critical, right? This is kind of what gives me my ability to polymorphically change things at runtime, right? If I change the function that a function pointer is pointing to, okay? Okay, so here's my goal. All right, I'm gonna keep with the duck theme, and I'm gonna say I want to be able to create ducks of different types. So you can see here in my pseudocode, I'm gonna make a rubber duck or a mallard duck. I want to be able to call the same function on both, duck show, but I want two different things to happen. I want each of these, derived classes, if you will, the mallard class and the rubber class, to provide different implementations. And I want this to be in the same source file, right? So I can't necessarily use my two techniques previously. Okay, so in order to be able to do that, what I know is that I need each of these objects, right? These classes, in this case, the George and Bill, which are objects of type mallard or type rubber. I need them to sort of hold a reference to the specific function that is meant to be called on them. So I need a function pointer that's part of the structure that I'm using to store information about my duck. Okay, so you can see here in duck.c, right? Previously, this was just the name variable. I'm going to add a function pointer that I'm going to call duck show. And so every instance of a duck will have, potentially a function pointer here that points to a different implementation of this show function. The header file is unchanged. Okay, so this is kind of like the key here, right? I've got a little function pointer that's part of my structure. And then you can see down here in my show function, I'm not just sort of printing a name, right? There's not just a static implementation. What I'm going to do first is check if there happens to be a valid pointer in this variable here. And if there is, then I'm going to call that function, whatever that function happens to be. And it's only if there isn't one here, which we'll sort of assume is kind of the default for like your generic ducks, that I give this kind of generic show function. So this allows each object individually to kind of override the implementation of duck show. And so I'm gonna pause really quick to kind of say that this gives us a couple of different types of inherited functions. We saw previously, maybe without realizing it, that an implementation that we might call final in C++ is just a base class with its own implementation. It doesn't check whether there's a function pointer in the structure. And so duck_quack is an example of that, right? This is a function that I don't want any derived classes to override, so there's just no spot in the structure for that function pointer. There's no check if that's there. The one we just looked at, you might call a virtual function, where there is a base class implementation if one isn't provided, but otherwise, if there is a function variable, then that's the thing that gets called on our objects. I can also make this a pure virtual function, which means there is no base class implementation. I have to have a function pointer, so I might even assert that there is a valid function pointer in each object, and then call that function on the object. A little later, we'll actually see kind of in C that you can mix kind of the final and virtual a little bit, which you might also call the template method pattern, where there is a base class implementation which is called, and also if a virtual function exists, then that is also called. So you might see some of these here in our code. Okay, so then let's, if we start making ducks now, they'll have this spot in the structure for the function duck show, but we don't yet have a way to sort of make that of a different type. Let's look at how we might do that. Okay, no change to duck.h. So I'm going to start making, let's say a mallard, right? Let's say I've got this mallard show function that I want to be able to use to describe these mallards. This is just going to come up with its own little, mallard specific show function. And the easiest way to do that initially is just going to write a little function here I call mallard init. You might just call it like, this is the function that sort of installs the virtual function in my object here. I'm going to assume that I have a duck that exists already, and I'm just going to set the variable duck show, which was a function pointer, to mallard show, right? So now when my duck code gets called, right down here, duck show will have a valid value. When that gets called on an object, which is, I'm going to call a mallard, it's this function which gets called. This can be a static function, right? File static, because I don't want this called directly. And you'll also notice here that in my header file, that's not present, but I do expose this mallard init function. So now what I can do in my main function is take a duck here, the third one called Louis. I can call mallard init on it. So this is going to sort of set the duck show function to mallard show. And now when I show my Louis, I'll get the mallard specific version. Okay, let me do this. So I want to go to, okay. So you see here now, I've got this mallard specific, show function, which is I was able to create by adding these two mallard functions that sort of took a duck and kind of made some mallard specific behavior. Now, the last piece that's critical to making this work is that you'll notice in these two functions, particularly in this one, my mallard needs to know the internals of my duck objects, which previously lived inside this source file, and that's not going to work because my mallard C file doesn't know what's inside my duck C file. I don't want to make those exposed necessarily to the rest of the program. So what I'm going to do is create a private header file. There's nothing, unfortunately, that prevents other users from looking at this and, modifying the internals of the duck objects directly. But then again, there kind of isn't either in C++, since those classes have to be defined kind of in the header files anyways. Hopefully by marking this as kind of an underscore private header file, we discourage anyone from referencing these details. So that got moved out of duck.c. You notice that little structure definition is no longer here. And now that it is in this private header file, in my mallard source file, I can include that and reference the internals of this structure directly. The last note here is that is about the fact that I'm reaching into this sort of duck object directly and referencing or manipulating the name variable or the duck show variable. You might argue that that sort of breaks the abstraction provided by the duck object. And if that was troublesome to you, then I've got a couple examples here of how you might provide sort of a layer of indirection in the private header file. I just noticed a lot of times this is useful in case the implementation of like this name variable changes. In the Mallard file, right, we're treating this very specifically as a string or as a function pointer. And so providing that little indirection can help make sure that I don't have to rewrite a bunch of code if one of those implementation changes. All right. Okay, so that this implementation actually is probably totally sufficient if my only goal is to take an object of some type and change around how the functions are implemented. But if I'm making a Mallard or making a derived class, then you might imagine that I want to actually start adding some data to it, right? I might have some Mallard specific data items that I want included in the structure that I want to actually operate on. You might have noticed here that my original example that, for my Mallard duck, I want to reference, whether it has what the feather color is or something like that. In order to do that, let's talk about pointers to data. And actually let me rewind real quick. I just also wanted to mention the idea of public, private, and protected functions. Because these are terms that you'll hear in object-oriented programming discussions. So we saw just in this last example that any public function, right, is something that I expose to the header file. Mallard show is an example of a private function because it's given the static keyword and I don't expose the function signature to the header file. And then we also, we didn't have any yet, but I give you in the comments there examples of what might be considered a protected function. This is a macro or an inline function that's defined in the private header file. So, ostensibly calling code has no access to it, but classes that are derived like a Mallard would, since they include the private header file. Okay, let's go back to talking about how I might add data to my Mallard object. So you can see here that C already has this idea that I can create pointers of different types to effectively the same spot in memory. Nums is an array of 5 integers, which is a very specific data type. Pnums is just a pointer to an integer. But here I initialize it to sort of the starting element in the nums array. So they both point to the same thing. But I can use them differently, right? And if I were to try to, use these to print some part of this array, the C compiler would be very specific about making sure the data types match. Okay, so let's think about how a duck is kind of laid out in memory. Right now I have a function pointer at the beginning, followed by a name, which is typically 10 characters in my examples. If I take a Mallard object and I make the very first element a duck structure, and I put any of my Mallard specific stuff after that, then in memory, you'll notice at the very bottom row, these are like the actual kind of like spots in memory where the stuff is stored. The very first part of a Mallard structure is identical to a duck structure. And it's just sort of after that where I get additional information. So it happens that if I have a pointer to a Mallard object, you see here in bold, that is also a pointer to a duck object because the duck object is the first element in my Mallard object, and the pointer to each of those are both point to the very first element in this structure. So I can sort of add data to my derived classes now by I'm going to go to Mallard C, right? I can create, I can kind of extend these structures by just making sure that the very first element is the base class. So in this case, a duck, and I can add my things like my feather color after that. Now to be able to use that, now I need a specific kind of function to like make a Mallard object, right? Because this is additional data that's being, has to have memory allocated for it. So I need my own little function here to kind of make my Mallard object, where I'm using, in this case, the heap memory to make that. And then I sort of I add my Mallard specific information where I'm setting the feather color in this case, and I'll get to this line in a second, but this is where I'm adding my Mallard specific functions. Okay, so now in Mallard.h, I've got my my new function that is able to create mallards, and in my show function, I'm able to reference that value specifically. So I can use now sort of the color variable, since this function is only ever called on Mallard objects. Now to kind of complete this picture, right, to effectively make these objects, I need to account for the fact that my my destroy function, right? My destroy function gets a little more. I can't use the duck function, right? Previously, I was able to destroy my mallards because they were all duck objects anyways using this one function. But I might have now different memory allocation, different deinitialization things that need to happen as objects are destroyed. And so I can't necessarily use this own function. I need sort of Mallard specific, derived class specific deinitialization and destroy functions. And once the Mallard object has been created, those functions can be included in my list of virtual functions here. So you'll see that in addition to having like a show function that is sort of overridden by my derived classes, I'm also going to provide deinitialization and destroy functions that are provided by my derived class. And in this case, it's kind of trivial, but you might imagine that if my derived class is a specific type of motor, right, there's might be specific things I need to kind of shut down that motor properly, or if I'm using static memory instead of dynamic memory, then the destroy function definitely needs to make sure that the specific memory pool I'm using is releasing information back to that array correctly. So when I add those, it's not strictly required, but it's very useful to take all of those virtual functions and put them into their own struct. So that's what you see here is I suck them out of the previous kind of duck object, and I made them their own structure, and I just made the first element in my ducks now a pointer to this structure. All right, and so the utility there is now in my Mallard source file, I can define a sort of single object of type of that interface type and define my functions one at a time. And then when I make my Mallard objects, I don't necessarily need to assign each one individually. I can just say, hey, this first element of the duck structure, which is a pointer to a bunch of virtual functions, that's going to point to this structure here, which has these functions all defined. The last thing I want to say about sort of creation and destroying is that this kind of happens in a bit of a W fashion, in the sense that, for instance, if I'm making a Mallard object, I definitely want the Mallard function here to be able to allocate the memory, because this is the only source code that knows kind of what elements are in there. But it might be that my base class has things that need to be initialized first. So what I need is sort of a base class specific initialization that can happen prior to any of my derived class initialization. So back in my duck file, right, that new function, I'm going to sort of suck out some of that code that was in here to kind of initialize this thing and put that now into my private header file as like a little protected function for initialization of ducks. And again, this is trivial. I'm just sort of copying something into the name, but again, this could be much more complex, where, you know, my base class represents a type of hardware sensor that has very specific initialization sequences that need to happen before a derived class of specific type of sensor does its kind of continual initialization. And then when I destroy things, I have to do that sort of in reverse order. So I'm going to go now to duck.c, and you'll see here now that in my destroy function, I'm potentially destroying ducks and or base class and or derived classes. If it's a base class, then I know what to do. I'm just going to sort of clear out the name and release the memory back to the heap. But if it's a derived function, which I'm identifying if there is a valid pointer in that that pointer to an interface struct, then I have to do this in sort of a reverse fashion, meaning first I deinitialize my derived class. You can see that here. Then I deinitialize my base class, which in this case is I'm just me clearing out the name array memory. And then finally, I call my destroy function on the derived class. So that would be releasing it back to the memory pool or something like that. And with that, I can now create objects of different types. So here you can see, instead of necessarily making this variable a duck and then converting it to a mallard, I can create mallard objects and then do duck things on those mallard objects. And I'll demonstrate that here if I go back to this folder. Okay. Now I can call mallard specific stuff on this object, and not only that, but I can use mallard specific information. So here this message includes the fact that Louis was made with red feathers, which you can see here. And I can deinitialize, I can destroy those objects correctly, and I can kind of wash, rinse, and repeat for many different classes. Okay, so the last thing I want to talk about is the idea of interface versus abstract versus base classes. So in many cases, what we might want to do with our ducks now is we don't actually want the user to make objects of type duck. We just want the code to treat all ducks the same, and we want to provide different implementations. So you can see here on my slide an interface class, an abstract class. In these cases, there is no official kind of constructor for these objects. In an interface class, I just define the functions that are being overridden by my derived classes. In an abstract class, I'm doing that, and I'm also specifying some member variables that must be included in each derived class. It's only when I include a constructor, which I have up to this point, that I can kind of consider this a base class. But like I said, let's imagine that I don't really want programmers to create objects of type duck. I don't want them to make a base class. I just want them to create mallard objects or whatever other specific type of duck objects I want. To do that, I just have to kind of get rid of the constructor. So you can see here now in part D, in my duck header file, I basically deleted the function called duck new that allowed me to create ducks. Nothing really changed in my private header or in my mallard file. This is all basically the same, but some code in my duck file now got a little more simple because I'm not having to deal with the fact that there is potentially a base duck implementation to worry about. In this version, there are no such things as ducks. Everything has to have a virtual table that represented the fact that it's a derived class. So that simplifies the code a little bit. Okay, so basically in that final example, we see here this little class diagram where I have an abstract duck implementation that I can't create specific ducks of, but I'm able to create two different types, mallard and rubber, and they override the show function. So they say they do mallard and rubber specific things when I call the duck show function, and otherwise provide all the functions needed to create and destroy those objects safely. And so you'll see in my, I'll go to my code now for main. You can see here now I'm making my ducks either mallard ducks or rubber ducks. I'm still calling the duck functions because those are sort of, supposed to be implemented by the base class, but they're doing mallard and rubber specific things. And if I go here, then I'll demonstrate that to you. Oops. There we go. Okay, here we go. So now you see this program running. You see specifically when I show these objects, they have rubber duck and mallard duck specific implementations thereof. So that's kind of a lot, honestly. Let's compare that with our previous polymorphic techniques. You'll realize that implementing runtime polymorphism is definitely the most difficult, the most complicated. But the advantage it gives us is that we can now, in one source file, treat objects of different types the same and have them provide their own implementations. Now, before we leave this topic, the last thing I want to encourage you to do is to keep it simple, to realize that runtime polymorphism is really cool. But in many cases, it's not exactly what's needed in the very common situation of writing some code for a microcontroller that uses a sensor. You might find that going all the way back to the very simple little singleton object with some type of build time polymorphism is really all you need. If your microcontroller is interfacing with a single sensor, and at build time what sensor that's going to be, even if it's one of many types, then you don't need anything more complicated than a singleton object with some type of build time polymorphism. It's only if you plan on having multiple sensors that you might need an opaque struct. But if there are multiple sensors of all the same type, right, I've got 3 or 4 of the same type of sensor, I still only really need my link time substitution. If I have different source files that interface with different types of sensors, then maybe I need an opaque struct with my compile time polymorphism. It's not unless I was writing code that in the same source file that I wanted to operate on different types of sensors. Or you can see kind of in the upper right hand, if I have like a sensor that I want my microcontroller to interact with based on potentially like some pull-up resistors that specify a hardware version, so it doesn't really know until it starts up what type of sensor that is, then I need to worry about runtime polymorphism. So keep that in mind as you're approaching your projects with these techniques in the future. All right, if you want to take these concepts further, there are a number of books that were helpful to me. Going through the head-first design patterns, even though it's written kind of for Java, was very helpful because I got to practice these techniques and sort of implementing those design patterns. The 2 books, Refactoring and Refactoring to Patterns, were also useful. Again, they're sort of assume a dynamically typed language like Java or C++, and so I got to practice my runtime polymorphism stuff in implementing those solutions. And I just recently found a cool website called Refactoring Guru that also shows different design patterns and refactoring solutions. Additionally, if you go to the GitHub, you'll see 2 examples of those design patterns using these techniques, and those are the template method pattern and the factory pattern. Okay, let's talk briefly about inheritance. This is a big concept, so like I said, I'm going to talk to you about the skills necessary to put this into place, but I'm not going to go into details because this could be a talk all on its own. So let's go back to this idea that I can have multiple pointers to the same piece of data. At the heart of this, the idea of creating inheritance structure is kind of extending the way I added data to my Mallard objects to just more and more objects, right? If I want to derive Mallard objects into a specific type of Mallard called a red Mallard, then I make sure that the first element of that structure is the Mallard object, which has a duck object inside it, and that all of my data comes after it. And I can do the same thing with my interface functions too. So we just saw a couple of projects ago that I have, maybe these 3 functions that define my duck interface: show, dinit, and destroy. If I have Mallard specific or red Mallard specific functions that I want to add to that, I can just sort of embed those interface structures inside each other to create this Russian nesting doll, these Matryoshka structs that kind of embed one another. So that's the crux, but I run into a bit of an issue with the fact that C is statically typed. So previously we sort of circumvented this by virtue of the fact that we were only kind of deriving our classes 1 level deep, and so I could just make every object of type duck. If I try to drive that further, then it gets a little weird. I don't necessarily want to make all of my objects like the same base object. So maybe I go back to an implementation where each of my classes returns its own data type. That works, but to me it gets a little clunky because now if I want to call this base class function on a Mallard, which is a derived class, I should be able to call it, the C compiler is going to complain unless I recast that Mallard object as if it were a duck object. So to me, this is not really polymorphic at that point because I still have to force the compiler to look at this thing differently than it was before. So one solution, the best one that I found, is to take all of our functions that make our objects and have them return a pointer to void, right? And C, this is a pointer to anything basically. So now I can call duck show on this, void pointer, because that's how I've written the function signature. You can see right here that duck show accepts a pointer to void. And basically in the first line of my code, I just recast this to be a duck. And this lets me, effectively what it does is it lets me totally circumvent the type system in C. And there's lots of bombs that come with that that we need to address. Well, two in specific. One, right? One is, how do I even know that this void pointer that I'm passing to this function is even a duck? You can see in this little pseudocode here. Maybe I'm making an object of a totally different type, and I'm trying to call this duck function on this object of a totally different type. So what this means is that my objects now, they have to contain information that points sort of upward in the class hierarchy, that effectively point to the base class. So if I have a random object, I can trace its lineage back to something that confirms that yes, it is a some object of type duck. This function makes sense. Well, really, the problem goes even further, because in order to do that, I'm taking the pointer, like in this example, in the first example, my car, and I'm assuming that it's a pointer to an object of some kind. And if I embed information there, I'm going to start dereferencing that pointer to sort of get at what the base class ultimately is. I don't even really know if it's an object necessarily. I mean, it would be very broken code, but a security concern definitely, that my duck show function is just accepting a pointer. And so even a null check doesn't work here, because this pointer has a value. It's just not pointing to an object. And if I start dereferencing that pointer, assuming that there are like elements to that are pointing to a base class, I might very well, wind up with some sort of segmentation fault or memory fault as I'm trying to reach into places in memory that don't exist. And the best solution to this that I could find is to include something called a magic number. And so what we're going to do is, for each of our object structures and for the interface structures, we're going to make sure that the very first element is just a hex number. The example the number that I stole from Axel Schreiner is hex 0EFFACED, which is kind of looks like the English word effaced. Effaced is to kind of make indistinguishable. And so what we're going to use this basically is now in these functions to even make sure that the void pointer that's coming in is a valid object. The first thing we're going to do is check, is it pointing to this number effaced? The chances of it pointing to that number, if it's not an object, are exceedingly small. And once we can confirm that, then we have to somehow sort of figure out whether some object, like, in this case, this duck pointer, actually inherits from duck at all. That's quite complicated. And so, like I said, I'm not going to go into the details, but I will direct you to the fact that you can see a couple implementations on the GitHub. So under the inheritance folder, you can see the Matroska structs, which is just making multiple structs and explicitly casting upwards and downwards. So you can see here some sample code in the main function of me casting between data types to make this all work, which, like I said, is kind of clunky. And then two implementations of that, of where we include the code that sort of checks whether an object is of a base class or not. So you can see one implementation that I did as a personal exercise to see if I could make it work. And then I have an adaptation of the code that Axel Schreiner did. And if this is of interest to you at all, I highly recommend that you check out either of these two documents. Axel Schreiner has a PDF called OOC, which is short for Object-Oriented Programming in C, where he basically comes up with a full implementation of C++ using straight C. It's very thorough, but it's also quite complicated. On the left is a copy of Mira Samek's book, Practical UML State Charts in C and C++. And if I'm not mistaken, in that book, he opts for sort of this style of inheritance where we are explicitly casting objects to one type or another. But he shows in that book how you can use that to build out full inheritance kind of structures. Okay, folks, thanks so much for your attention. That's all I got. I just want to summarize real quick by making sure this is kind of the thing you take away from today, right? We talked about the four precepts, the four principles of object-oriented programming, which were abstraction, encapsulation, polymorphism, and inheritance. I showed you a number of ways that you can apply those techniques to your code using the singleton and opaque structs to provide encapsulation, using linker substitution, the preprocessor, or function pointers to create either build time or runtime polymorphism. And we didn't get too deep into inheritance, but I showed you how you can use sort of Matryoshka structs and sort of create your own type system to implement inheritance. And along the way, I showed you a number of examples where you can apply those techniques. 3, the mediator, the template pattern, and the factory are all sample projects you can find on GitHub. And we took a look at how even just, some simple encapsulation and linker substitution can give us the ability to build a functional simulator. That's all I got. I've taken enough of your time. Thanks so much for your attention. Enjoy the rest of the conference.